Hello everyone, today we'll be doing a short introduction to polynomials, and we'll be covering the definition of some terms related to polynomials and also some examples covering some of these terms. So let's start with a couple of definitions. So first, a term is a single number, a variable, or the multiplication of a number and a variable or multiple variables. So for example, the number 5 is a term because it's a single number. X is also a term because it's a variable, a single variable. Something like 3x is also a term because it's the multiplication of a number and a variable. And 3x is the same as saying 3 times x. But in algebra, the multiplication sign is not seen. So we just write 3 times x as 3x. So any case where we multiply a number and a variable or multiple variables, we just remove the multiplication sign and write down the number and variable together. So something like 10x, y, z, which is also a term because it's the multiplication of a number and three variables, x, y, and z, is just the same as saying 10 times x times y times z. So these are all examples of terms. And there's another way we can refer to these terms. We can call them monomials because monomials are mathematical expressions with only one term. So these are all monomials. So moving on, let's move on to the definition of a binomial, which is a mathematical expression with two terms. So examples, let's say x minus 5. This is an example of a binomial because there are two terms in this expression. Something like x cubed minus x. That's also an example of a binomial because there are two terms. Then a trinomial is a mathematical expression with three terms. So something like, let me use a different letter. Let's say y squared minus y plus 1. This is an example of a trinomial because there are three terms. We have y squared, we have y, and 1, three terms in total. So this is a trinomial. And something like, let's say b cubed plus b squared minus 8. This is also a trinomial because there are three terms in this expression. And then finally, we have a polynomial, which is a mathematical expression with many terms. So something like 6x raised to the power of 4 plus x raised to the power of 3 minus 8x raised to the power of 2 plus 5. This is an example of a polynomial because it has 1, 2, 3, 4 terms. So this is classified as a mathematical expression with many terms. So this is an example of a polynomial. So oftentimes trinomials and binomials can also be called polynomials. So let's say 5x squared plus 4. So even though the correct term for this expression would be a binomial, sometimes people can also call them polynomials because it's an expression that has more than one term. So it's not wrong to call it a polynomial, but technically the right term for this expression would be a binomial. Same with something like x squared plus x squared plus x. This expression is a trinomial, but you can also call it a polynomial because it's also an expression with many terms. So these two, even though they can be referred to a binomial and a trinomial respectively, they can also be called polynomials as well. Just something to note. So Another important thing I want to say regarding binomials, trinomials, and polynomials is that they can be defined as a combination of terms linked with plus and or minus signs. So let's look at these other examples. So we can see here that this expression y squared minus y plus 1 is linked by a minus sign and a plus sign here. So that's another way we can differentiate these expressions from terms. So notice like with a term, with these terms here, there's no plus or minus sign anywhere. It's just 5x, just single terms on their own. So that's something to note when distinguishing terms or monomials from binomials, trinomials, and polynomials. So with a binomial, we have two terms, x and 5, and they're linked with this minus sign in the middle here. So that's a way to differentiate monomials from binomials. Just look out for a plus or minus sign and you can tell whether it's a monomial or it's a binomial, trinomial, or polynomial. Okay, so now that we know the definition of these different expressions, I want to define some other terms as well. So first we have the definition of a degree, and the degree of a term, first of all, is the sum of exponents in a term. So example, let's say we have, let's use a different color. Let's use purple, say x squared. And we have to find the degree of this term x squared. So we can see that x is raised to a number here, which is 2, and 2 is the exponent of x in this case. So knowing that the degree of a term is the sum of exponents in that term, the degree of this term x squared is 2 because x is the only variable in this term, so there's no other variable or number to consider. So the degree of x squared is 2. Same with something like y raised to the power of 3. Since y is raised to this number, 3, the degree of this term y raised to the power of 3 is equals to 3. So let's say we have something like 5x squared, and we have to find the degree of this term. So x squared, we can see that x is raised to the power of 2, so we know the exponent of x, but what about 5? So 5 is a coefficient of x squared in this case, and usually with coefficients, they don't have degrees, so we can say that the degree of this term is 2. But we can actually get more technical about this and prove that the degree of 5x squared is equals to 2. So let's let's go about that. So let's say 5x squared, and we have to find the degree of this term. So something to note is that any number of variable that is raised to the power of 0 is 1. So we can actually rewrite this 5 to accord with this rule. So we can say that 5 is the same as 5. And since we're working with the variable of x, we can use x. And x will be raised to the power of 0. And then we have x squared. And what this means is that since x is raised to the power of 0, anything that is raised to the power of 0 is equals to 1. So we can say 5, and x raised to the power of 0 will be equals to 1. So 5 times 1, and then times x squared. And if we multiply this out, 5 times 1 is 5, and then 5 times x squared is just the same as writing the number and the variable together. We can ignore the multiplication sign. So this is how 5x squared is the same as saying 5 times x raised to the power of 0 times x raised to the power of 2. Because any variable is raised to the power of 0 is 1. So when we have 5x squared, there's an invisible x raised to the power of 0 there. So that's why when we have coefficients in front of variables, we usually disregard the coefficients and focus on the on the exponents of the variables. So knowing this, the degree of 5x squared, now that we know that 5x squared is equals to 5x raised to the power of 0 times 5 raised to the times x raised to the power of 2, I'm so sorry. So if we look at this term now, the degree of this term, so looking at these two values, these two variables, we have x raised to the power of 0. So we have 0 as the exponents of the first x. And then we have x squared. So the exponents of the second x is 2. So x plus 0 plus 2. And 0 plus 2 is 2. So that's how we arrived at 2 in both cases. So again, when we have coefficients in front of variables and we have to find the degree of that term, we usually don't pay attention to the coefficients and just focus on the variables. But this just shows, I just gave a more like technical way and explained why that is so. So let's go do another example just to make sure it makes sense. So let's say 6x. And we have to find the degree of this term. So looking at this, we can see that there's no number that x is being raised to. We can't see an exponent of x, but we don't need to worry about that because any number that is raised to the power of 1 is the number itself. So if we have something like 2 raised to the power of 1, that is equals to 2 because any number raised to the power of 1 is the number itself. So 2 raised to the power of 1 is equals to 2. Same with 5. 5 raised to the power of 1 is 5. And I don't know, 1,000 raised to the power of 1 is also going to be 1,000. So any number raised to the power of 1 will always be that number. So with 6x, knowing that x is on its own, we can say that 6x is the same as saying 6x raised to the power of 1 because x raised to the power of 1 is x itself. So the exponent of x in this case is 1. And since 6 is a coefficient, we don't need to consider it. We can focus on the variable x. So the degree of 6x is equals to 1. Let's give another example. We have 10x squared times y. So now we're working with two variables here. We have x and y, and they're being multiplied with the number 10. So 10 we can disregard because it's a coefficient, is a constant. We don't need to consider 10, and we can focus on x squared times y. So here we can see that x is being raised to the power of 2, so we know that the exponent of x is 2. And then y, we just discussed that any number is raised to the power of 1 is the number itself. So y is the same as saying y raised to the power of 1. So the degree of this term will be equals to 2 plus 1, and that is equals to 3. So these are just a couple of examples. I will go more in depth. We'll have a couple of examples that will have us find the degree of those terms. I will have some practice with this in a couple of minutes. So this is also something that I will cover later. The degree of a polynomial refers to the highest of the degrees in the polynomial, which in other words, the monomial of the term with the highest exponent. So for example, let's say we have 6x raised to the power of 4 plus x squared minus 8. So let's go over these terms one by one. So we have 6x raised to the power of 4. So what is the degree of this term on its own? So since 6 is a coefficient, we can disregard that and focus on x raised to the power of 4. And the exponent of x in this case is 4. So the degree of this term is 4. And then we have the second term, we have x squared, and x is a variable and it's on its own, and it's raised to the power of 2. So the exponent of x in this case is 2. So the degree of this term is 2. And then we have 8 here. I remember that 8 is a constant, it's a number, so it's a constant. So 8 is the same as saying 8 times x raised to the power of 0, because x raised to the power of 0 is equals to 1, and 1 times 8 is equals to 8. So now that we've rewritten 8 as 8 times x raised to the power of 0, we can consider the exponent of x, and that's 0. So the degree of this term is 0. So now we have the degrees of all the terms. So looking at this, we know that 4 is the greatest of the three numbers here. So since 4 is the greatest number, that is the degree of the polynomial. So this polynomial is called a fourth degree polynomial. And that's because the highest degree in this polynomial is 4. So it's called a fourth degree polynomial. Also, the term 6x raised to the power of 4 is the term with the highest exponents. So that's the reason that it's called a fourth degree polynomial. Okay, so the last two terms I want to explain are leading terms and leading coefficients. So a leading term is the term with the highest degree. So using the example we just used, let me go back up. That was 6x raised to the power of 4 plus x squared minus 8. Let me rewrite it down here. 6x raised to the power of 4 plus x squared minus 8. So a leading term is the term with the highest degree. So we just discovered that 6x raised to the power of 4 is the term with the highest degree because 4 is the greatest number out of all the exponents here. So the leading term in this expression is 6x raised to the power of 4. This is the leading term. And furthermore, we have what is called the leading coefficient, and that is the coefficient of the leading term. So a coefficient, for anyone that doesn't know, is the number that is in front of a variable. So in this case, the variable in this term is x, and the number in front of x is 6. So the leading coefficient is 6 in this case, because that's the coefficient of the leading term 6x raised to the power of 4. So 6 is the leading coefficient. And again, this is where I was explaining the definition of these terms and giving some short examples as well. It's okay to if you don't understand it at first, because we are going to go over a couple of examples that have us find the leading term, the leading coefficient, degrees, whether it's a monomial, binomial, a trinomial, polynomial, and other things. So let's start with this example first. So we have this expression that says x raised to the power of 4 minus 3x raised to the power of 3 plus 2x raised to the power of 2 minus x plus 5. So let's start by counting the number of terms in this expression to determine what kind of expression that it is. So we have 1, 2, 3, 4, and 5. So this is an expression with 5 terms, and based on the definitions, we can call this a polynomial because a binomial only has 2 terms in it, and a trinomial has 3. But a polynomial is an expression with many terms. So since this has 5, we can classify this as a polynomial. So this is a polynomial. So let's move on and try and find the degrees of each individual term in this. So let's start with x raised to the power of 4. So x is raised to this number, the number 4. So that's the exponent. So the degree of this term is equals to 4. That's the first term. And then we have the second term, negative 3 raised to the power, negative 3 raised times x raised to the power of 3. So again, we have a coefficient of 3, which we can disregard because negative 3 is the same as saying negative 3 times x raised to the power of 0, because x raised to the power of 0 is 1, and 1 times negative 3 is negative 3. So this expression is the same as writing negative 3 times x raised to the power of 0 times x raised to the power of 3. So if we find the degree of this, we have two x's here. The first x is raised to the power of 0, so we have 0. And then the second x is raised to the power of 3, and then we have plus 3. So the degree of this is 0 plus 3, and that's 3. And then the third term, we have 2 raised to the power, 2 times x raised to the power of 2. Again, we can disregard the 2 and focus on x squared. So x is raised to a power of 2, so the degree of this term is equals to 2. Okay, and then let me draw a divider. We have negative x, and recall that any term that is raised to the power of 1 is the number itself. So in this case, negative x is the same as saying negative x raised to the power of 1, because negative x raised to the power of 1 is just negative x. So we have negative x with a power of 1, an exponent of 1. So the degree of this term is equals to 1. And finally, we have the number 5. And 5 is the same as saying 5 times x raised to the power of 0, because x raised to the power of 0 is 1, and 5 times 1 is equals to 5. So this is just basically the same thing. And since x has a power of 0, then the degree of this term is also equals to 0. So in general, constants, numbers on their own have degrees of 0. Let me put that as a note. Numbers on their own have a degree of 0. So just something to remember in case uh, you get confused with numbers on their own and you have to find the degree of that number. They're all equals to 0. So now we know the degrees of all these terms. What is the degree of the polynomial overall? So the degree of the first term is 4. Let me use a different color. The degree of the first term is equals to 4. The degree of the second term is equals to 3. The degree of the second term, of the third term, I mean, is equals to 2. The degree of the fourth term is equals to 1. And the degree of the fifth term is equals to 0. So we have 5 different degrees. So let's write them out. We have 4, 3, 2, 1, and 0. So recall that the degree of the polynomial is the degree of the monomial with the highest exponent, with the highest power. So of these 5 numbers here, we can tell that 4 is the biggest number. So this polynomial is a 4th degree polynomial. It's a 4th degree polynomial because it has the highest exponent in the polynomial is 4. So it's a 4th degree polynomial. So since we know that the highest exponent is 4, The term that had the exponent of 4 was x raised to the power of 4. So that is our leading term because it's the term that had the highest exponent. So x raised to the power of 4 is our leading term. Okay. And since x raised to the power of 4 is the leading term, the leading coefficient is equals to 1 because x raised to the power of 4 is the same as writing 1 x raised to the power of 4. So just as how a number being raised to the power of 1 is the number itself, any number times 1 is also the number itself. So 5 times 1 is equals to 5. 10 times 1 is also equals to 10. So you can see in these cases, any number times 1 is just the number itself. And this goes for variables as well. So 1 times x is also x as well. So the coefficient of x raised to the power of 4 is 1. So 1 is the leading coefficient. 1. 1 is the leading coefficient. Okay, so this was one example where we had to find what kind of expression this example was, the degrees of each individual term, the degree of the entire polynomial, and then what the leading coefficient and term was. So let's try another example. So we have this. We have this expression, 6y raised to the power of 6 minus 3y raised to the power of 3 plus y minus 10. So again, let's count the number of terms in this. So we have 1, 2, 3, and 4 terms. So since this is an expression with 4 terms, you can call this a polynomial. This is called a polynomial. So now let's find the degrees of all individual terms. So let's start with 6y raised to the power of 6. So we can disregard 6 and focus on y raised to the power of 6. Since y is raised to the power of 6, that's the exponent of y. So the degree of 6y raised to the power of 6 is 6. Okay. And then the second term is negative 3y raised to the power of 3. So again, we can disregard 3 and focus on y raised to the power of 3. It is raised to a number 3. So the degree of this term is equals to 3. And then the next term is y plus y. And recall that any number raised to the power of 1 is the number itself. So y is the same as saying y raised to the power of 1. And since it's raised to the power of 1, that's its exponent. So the degree of y is equals to 1. And finally, we have negative 10. And negative 10 is a number, it's a constant, and any constant has a degree of 0. So the degree of the last term is equals to 0. So now we have these 4 degrees of the 4 terms in this polynomial. So based on this, we can find the degree of the polynomial overall. I remember the degree of the polynomial is the degree of the number with the highest exponent. So looking at these 4 numbers, we can tell that 6 is the highest of these 4 numbers. So therefore, the degree of this polynomial is 6. So this is a 6th degree polynomial. So the degree of the polynomial is based on the highest exponents of the monomials in the expression. It is not based on the number of terms in the polynomial. So we can see here that this polynomial had 4 terms here. So that doesn't mean that it's a 4th degree polynomial. No, We have to find the degrees of all the terms in the expression and then deduce the highest of those degrees to find the degree of the polynomial overall. So based on the degrees of all the terms, we discovered that 6 was the highest. So this is a 6th degree polynomial. Okay, so now we know that this is a 6th degree polynomial. Let's find the leading term and coefficient. So since we know that 6y raised to the power of 6 has the highest degree of 6, so 6y raised to the power of 6 is the leading term. Scroll down. So 6y raised to the power of 6 is the leading term. And it's the leading term because it has the highest exponent. Scroll down a bit. It's the leading term because it has the highest degree. Good. And since 6y6, it has a coefficient of 6 in front of it, so the coefficient of 6y raised to the power of 6 is 6. So 6 is the leading coefficient. So 6 is the leading coefficient because it's the coefficient of the leading term. All right, so this was just another example where we had to find the degrees of the terms, degrees of the degree of the polynomial, the leading term, and the leading coefficient. So let's do another example. So we have this expression. So something to note is that in the other expressions that we've been working with, we've had the luck of having the terms being arranged in descending order. And what I mean by that is, say we have this. Say we have this polynomial. So looking at the powers, let's focus on the x part of these terms. So looking at this, we can see that the powers of x are decreasing. So the first term has a power of 4. The second term has a power of 3. The third term has a power of 2. The fourth term has a power of 1 because anything raised to the power of 1 is a number itself. So there's a 1 here. And same with 7. 7 is the same as saying x raised to the power of 0 because x raised to the power of 0 is 1. 7 times 1 is equals to 7. So we can see that the exponents of x are decreasing with each term we write. So this is a common practice that we want to deploy when working with polynomials, even though it's not necessary, but it is advised that we write polynomials in descending order for the sake of clarity so that we're not missing any terms in the expression. So it's important to write polynomials in descending order. So in this case, we have an expression, but we can see here that we have y raised to the power of 2 in the middle. We have y raised to the power of 6 as the third term. So we can see that the expression is out of order. So we want to rewrite this expression. So since looking at this expression, we can see that y raised to the power of 6, 6 is the largest number here. So we can rewrite this and have y raised to the power of 6 as the first term. And then the next highest degree is 3 times y raised to the power of 4 because 4 is the next largest number. So you can say minus y raised to the power of 4. And then the next highest degree is 2. So 5y times raised to the power of 2. So we have negative 5y2. And then the last term is 10. So we have plus 10. So what we've done is just rewritten the polynomial with the exponents going in descending order. So again, it's important to just try and have this practice because it's helps for clarity's sake. It helps in reading polynomials better, so you're not missing some important key terms in the middle of the expression. So now that we've rewritten this, let's count the number of terms in this expression. We have 1, we have 2, 3, and 4 terms. So since we have 4 terms, this is a polynomial. This is a polynomial. So now let's go ahead and find the degrees of each term. So let's start with the first term, y raised to the power of 6. So since it's raised to number 6, the degree of this term is equals to 6. And then the next term is negative 3y raised to the power of 4. We can disregard 3 and focus on y raised to the power of 4. And since it's raised to this number 4, the degree of this term is equals to 4. And the next term is negative 5y raised to the power of 2. We can focus on y on its own. It's raised to this number 2. So the degree of this term is 2. And finally, we have 10. And 10 is the same as saying 10x raised to the power of 0. It's the same thing. And since x, oh, I said x, I'm so sorry. I meant to say y because all the terms in this expression are in terms of y, so there should be 10y raised to the power of 0. So since the exponent of y is 0, the degree of 10 is equals to 0. So now we know the degrees of each term. We can identify the degree of the polynomial overall. So out of these 4 numbers here, the highest number here is 6. 6 is the highest number. So therefore, that means that this polynomial is a 6th-degree polynomial. So this is a 6th-degree polynomial. Again, the degree of a polynomial is not based on the number of terms because this polynomial has 4 terms. So this is not a 4th-degree polynomial. It's a 6th-degree polynomial because the degree of the term in the expression was 6. The highest degree of the monomial in this expression was 6. So therefore, it's a 6th-degree polynomial. So now let's find the leading term and coefficient. So since we know that the highest degree of all the terms in this expression was 6, we considered the term that had 6 as a degree, which was y raised to the power of 6. So therefore, y raised to the power of 6 is the leading term because it had the highest degree of 6. And again, I want to point this out because now that we know that y raised to the power of 6 is the leading term, if we look at the original expression, we can see that 10 was the first term in the expression. So usually the leading term of the expression is the term that is mentioned first, but in this case, the leading term was mentioned third, was listed third in the expression. So it's important. That's also another reason why it's important to rearrange the expression to make sure the terms are listed with the exponents in descending order, because it's common to have students make this mistake. So in this case, the leading term was not the first in the expression. So we need to rearrange it to make sure that the terms are listed with the exponents in descending order to determine the leading term. All right, and now that we know what the leading term is, we can find the leading coefficient. So y raised to the power of 6 is the same as saying 1 y raised to the power of 6. So based on this, we can tell that the leading coefficient is equals to 1. because that is the coefficient of the leading term. So that is the leading coefficient. Okay, let us go over one more example where we have to find the degree of the polynomial, the degree of the terms, and the leading term and the coefficient. All right, so in this expression, we are working with terms that have multiple variables being multiplied. So the first term, we have two variables, x and y, being multiplied. The second term, we have y and z being multiplied. And the third term has three variables being multiplied, x, y, and z. So let's go over each one by one. So first of all, let's find the number of terms in this expression. We have 1, 2, 3, 4 terms. And since it's a expression with 4 terms, it's a polynomial. So let's go over each term individually and find the degrees of each term. So degrees. So the first term is x squared times y. So this is the same as saying x squared, and y it's on its own, but y is being raised to the power of 1 here because y raised to the power of 1 is y on itself. So this is the same as saying x squared times y raised to the power of 1. So we have the exponent of x here, which is 2, and the exponent of y, which is equals to 1. So the degree of this term is just the sum of these two exponents. So 2 plus 1 is equals to 3. So the degree of x squared times y is equals to 3. So let's move on to the second term. We have y times z raised to the power of 3. So y, in this case, is being raised to the power of 1. And then we have z c raised to the power of 3. So we have two exponents, 1 and 3, and the degree of the term is the sum of these exponents. So 1 plus 3 is equals to 4. So the degree of y times z raised to the power of 3 is 4. Okay, and the next term is negative 4xyz. So we have three variables here, and each of these variables are being raised to the power of 1. These are all being raised to the power of 1. So the sum of the exponents is just 1 plus 1 plus 1. And that's equals to 3. So the degree of this term is 3 as well. And then the final term is equals to 7. And 7 is the same as saying 7 x raised to the power of 0. Let me remove this. The same as saying 7 times x raised to the power of 0 times y raised to the power of 0 times z raised to the power of 0, because we're working with three variables here, but even so, they're all being raised to the power of 0, and anything raised to the power of 0 is equals to 1. So this is the same as saying 7 times 1 times 1 times 1, and that is still equals to 7. So regardless, since all the exponents of these variables are 0, 0 plus 0 plus 0 is equals to 0. So regardless, the degree of 7 is equals to 0. Okay, so now we know the degrees of all these terms. Let's find the degree of the polynomial. So looking at these four numbers, 3, 4, 3, and 0, we can see that the highest number here is 4. So this means that this is a fourth degree polynomial. And I actually did forget to rearrange this polynomial because we can see now that 4 is in the middle. So 4 should have been the first degree, so that 4 would have started off, we'll have had 4, 3, 3, and 0. So the degree should have been in descending order. So This shows why it's important to rearrange a polynomial so that the exponents are in descending order, because we can see now that this is a fourth degree polynomial. So a common mistake would have been to assume that it would have been a third degree polynomial. So let me rearrange this. All right, so if we were to rearrange this based on the degrees of the expression in the original question, let me erase all this. So looking at this, we know that we can see that the first term has a visible degree of 2. We can see the second term has a visible degree of 3, and then we have the third and the fourth term. So looking at this, 3 is the highest visible term we can see here. So we can rewrite this expression and have y times z raised to the power of 3 as the first term. You know what? Let me write it up here. So y times z raised to the power of 3 is the first term. And then the next highest visible term we can see is x squared times y. So that can be the second term. And then the next highest would be 4xyz. And then finally we have plus 7. So here is just us rewriting the degrees. Sometimes it may be a bit difficult to tell because of course, we're working with 3 different variables, x, y, and z, and each variable has its own exponent as well. So it may be a bit hard to tell which one has the highest degree at first glance. But if we go over each term individually and consider all the terms, we can deduce which has the highest exponents, the highest sum of exponents, the highest degree. And in this case, it was 4. And that was for y times z raised to the power of 3. So that's how we can tell which has the highest degree, and we can rearrange it as well. So we know that this is a fourth degree polynomial. So let's find the leading term and the coefficient. So knowing that 4 is the highest degree of all the monomials in this expression, the term that had 4 as the degree was y times z raised to the power of 3. So that means that that is the leading term. So this is the leading term. And then the coefficient of this is the leading coefficient. And since there's no number in front of it, we can say that there's a 1 here because 1 times this expression is the same as the expression itself. So 1 is the leading coefficient. Okay, and that has been some examples relating to polynomials, having to find the degree of the polynomial as well as the degrees of each term in that polynomial, having to find it, the leading term and the coefficients as well. So this is just a short introduction dealing with polynomials. We also can add and subtract polynomials. We can work with monomials and trinomials. So I hope that this recording helped you understand polynomials better. Like I say, it's always important to practice, so you can just whip up some polynomials to practice on. Try looking at each term individually, finding the degree of each term, and then using that to find the degree of the polynomial as a whole, find the leading term and the coefficient. So I would advise that you find some polynomials to practice on and try and find all these things. So I'm hoping that this short video helped you understand polynomials better. So thank you so much for watching this video.